Hello and welcome to the Chemistry Academy. In this video we're going to be looking at transition metal complexes as part of the Advanced Higher Chemistry course. So we're going to look at what they are, how we name them, the oxidation, working out the oxidation number for the transition metal within the complex, talk a bit about coordination number, and then we'll also finish off with talking about the different colours that we observed in transition metal complexes and why we observe different colours. So to get started, we'll talk about what they are. So a transition metal complex is essentially where you have a substance that has a central metal ion that's surrounded by things that we call ligands. So ligands are just groups of atoms or individual atoms that either have a negative charge or they have a lone pair of non-bonding electrons. And you would have talked a bit about lone pairs of electrons when you did valence shell electron repulsion theory, or electron pair repulsion theory. So you should be familiar with which atoms or molecules tend to have lone pairs of electrons on them. So there's a couple of complexes I've drawn here. So this is what you would characteristically see a transition metal complex being drawn like. They will usually have square brackets around them, and sometimes you can have ions that are outside of the complex, but these things around the central metal are what we would call the ligands, so the groups of or atoms attached to the central metal. When it comes to ligands, we get different classifications of the ligands. It's based on these terms of dentate, so we've got monodentate, bidentate, tridentate, etc. And dent is Greek for teeth, which is why you go to the dentist. So when it says monodentate, it means there's like one bite to the metal. So anything that's monodentate will form one bond to the central metal ion. Anything that's bidentate will form two bonds to the central metal, and anything that's tri would be three. It goes up to hexadentate, which is six, and that the hexadentate ligand is this EDTA that you'll quite often use in your transition metal complexometric titrations. That's usually what we use as the standard solution. You don't really need to know much about the EDTA other than recognise its name and know that it binds to metals, and know that there's always a 1-to-1 ratio between the metal ion and the EDTA ligand. This is its full name here, ethylene diamine triacetic acid, but you don't need to remember that. Everyone affectionately calls it EDTA. So as long as you can remember that abbreviation, that's all you need to really know. And like I said, remember that it's always a 1-to-1 ratio with the metal ions that it's making the complex with. So some of the common ligands that you will see are like chloride ions, ammonia molecules of water. And when we're talking about transition metal complexes, water is usually always written as OH2 rather than H2O. The reason for that is because it's the oxygen that bonds to the central atom, so the central metal atom, so they want to show the bonding atom first. So just bear that in mind when you do see water as a ligand within a transition metal complex. It will be written as OH2. It still makes me feel a bit weird every time I see it because they only changed it a few years ago. So you will see in older past papers it written as H2O, but don't write it as that in the current day because we've moved on, and I don't know why they changed it. They did. You've got then the cyanide ion, then nitrite. So these names I put here are not the names of the ions, but this is the names that we give the ligands once they're in the complex. So we will look at naming some complexes, but these are the names of the ligands once they are within the complex, and you're not probably going to have to name them outside of a complex. So it's more useful to probably have their names while they're in the complex. So chloride, when it's in a transition metal complex, becomes chlorido. The ammonia becomes amine. Water is named as aqua. The cyanide ion is cyanido. The nitrite is nitrito. And then we've got, you could have iodide ion in a complex, that would be iodido. If it was bromine, a bromide ion, it'd be bromido. You get the idea where the ido comes from. So any ion that usually would end in ide, you just change the ending to ido. Same with hydroxide. If there's a hydroxide ion in the complex, you would call it hydroxido in the name. Okay, then so these are all our monodentate ligands, which all form one bond to the metal. Then we've got a bidentate ligands. So these are ones that form two bonds. The most common one you'll get is oxalic or oxalate, which is essentially just oxalic acid that's lost its protons, the H plus positive hydrogens. In a complex formula, it will be written as this, O2C2O2, and just bear in mind it has a 2 negative charge. In the name, it will be oxalato. Oops, let's cross that L, it shouldn't be. So oxalato is what its ligand name would be once it's in the transition metal complex. We've also got another example of a ligand, a bidentate ligand here, the 1,2-diaminoethane. So it can form two bonds with by the nitrogen atoms. You won't really probably see this in a complex that you need to name, and you probably won't see it in a shortened structural formula of a complex either. So you just might have to recognise it as a ligand in a drawn complex. And then I've already spoken about EDTA. So in terms where these ligands actually bond to the metal, it'll either be through their negative charge, so the chloride and all these bond by the negative charges, or the bonding site is where the negative charge is. For these ligands here that we class as neutral ligands, they bond using their lone pairs, or one of their lone pairs of electrons. So that's where the binding site would be in those instances. The neutral ligands, they bind to metals a bit differently to the ion ones. So the ion ligands with the negative charges will bond just by like ionic bonding that you learned at National 5. But the neutral ligands form these special types of bonds that are called dative covalent bonds. So you need to know the definition of that. And a dative covalent bond is just a bond in which both of the bonding electrons have come from the one atom. So in the case of the ammonia, both bonding electrons have come from the lone pair on the nitrogen. In this complex here, you can see these waters are all bonded to the iron. It's the oxygen donated two bonds to form, two electrons to form that covalent bond. So make sure you know the definition of a covalent bond, because you will often be asked outright in the exam state what's meant by a dative covalent bond. So it's where both of the bonding electrons have come from the one atom. So that's how the neutral ligands bind to the metal. They donate a lone pair of electrons in order to form a dative covalent bond. So if we then go on to looking at how these are then written as formula, first of all, so the chemical formula for transition metal complexes always has the central metal atom first. So in this case it would be copper. I'll use a blue pen for this actually. And then the ligands go in alphabetical order after, but there's only one type of ligand here. So the ligand is chloride, and there's 4 of them. So it would be Cl with a bracket of 4, and then it always goes in a square bracket. So the full formula goes in a square bracket, and any overall complex charges then goes outside the square bracket. So that would be the chemical formula for this complex up here. For this one, we've got iron as the central metal ion, and then we've got 6 water ligands. So again, remember I said before, you have to write it as OH2, and there's 6 of them, so we put a 6 on the outside, and then again the whole thing goes in square brackets, and we put the overall complex charge on the outside of the square brackets. So that's our formulas for those two. It's pretty straightforward. That's not really a skill that you're asked to do much though, is writing a formula for a transition metal complex, but it's still a handy skill to have. The more common things you get asked about are these 3 things here: the oxidation state, the coordination number, and then the name of the complex. So if we look at the oxidation state first, so I have done a previous video on oxidation states of transition metals, so you can go and have a look at that if you would like a bit more background on it. But essentially what you're trying to do is work out how many electrons the metal has gained or lost. And usually for metals, it's always that they've lost the electrons. And the reason that they lose electrons is by binding to these negative charged ligands. So the chloride, or the chlorido ligand, has a 1 negative charge, which means that they've essentially taken 1 electron each off the copper. So if we've got 4 chloride ions that have taken an electron off the copper, then that means the copper is going to have had 4 electrons taken off it, which would make it 4 plus. Okay, because if I write the charges on here, just so you can see that's 1, 2, 3, 4 minus, so that would have to be 4 plus to balance that out. However, there's a 2 negative charge overall, so that's like adding 2 electrons back on, so it's like giving the copper 2 extra electrons. So although it originally would have had 4 taken off, something on the outside has been like, here, have an extra 2 electrons. So that means that it actually has only really lost 2 overall. So like these negative charges on the outside are kind of like a savings account, if you like. It's like extra electrons you can use. So that's how I tend to work out the oxidation state. There are slightly other ways to do it, but that's just the way that's worked for me in the past. So the oxidation state of the copper in this complex would be 2 plus, or you can write it as plus 2, but it's essentially what the charge of the metal is. If we then look at the iron, so water is one of our neutral ligands, which means it doesn't actually affect the oxidation state of the metal, so it doesn't take any electrons off the metal atom, because remember, it bonds with it by donating its lone pair of electrons to form that dative covalent bond. So because all of the ligands are neutral ones, essentially this iron has an oxidation state of 0. However, there's a 2 plus on the outside here, which means 2 electrons have been taken away somewhere else by something else. So that means that the iron actually is in a 2 positive state. So it's, again, oxidation number will be 2 plus. So when there's a negative charge on the outside of the complex, that's like giving extra electrons to the metal. But when it's a positive charge on the outside, that's taking additional electrons off of the metal on top of any that have been taken off by the ligand. Okay. If we then move on to coordination numbers, so coordination numbers, the easiest one is essentially how many bonds have been made to the central metal ion. So all you have to do to work out the coordination number is count how many bonds exist around there. So we've got 1, 2, 3, 4, so that's coordination number 4. On this complex, we've got 1, 2, 3, 4, 5, 6, so that's coordination number 6. So if you get a coordination number question, it's usually a pretty easy mark. And then that brings us on to the name. So the name, we start off with the ligands, and they have to be in alphabetical order. In this one, it's a bit, these examples are straightforward because there's only one type of ligand. We'll do some more examples after this where we've got other types of ligands. So for this first one, it's chloride or chlorido, and there's 4 of them. So we would have the prefix tetra in front. So tetra chlorido. And then after you've named the ligands in alphabetical order, if there's more than one type, we then add the name of the metal. So this is copper. However, the overall complex is negative, which means that we have to change the name ending of the metal to 8. And for copper specifically, we revert back to its Latin name and change it to cuprate. So if copper is in a negative, overall negative complex, you need to put it in the name as cuprate. And so tetrachloride or cuprate, and then the oxidation state has to go in brackets at the end. We work that out to be 2 positive, so we put a Roman numeral 2. So this complex is called tetrachlorido cuprate 2. If we then look at this one, we name our ligands first. Our ligand is aqua, and there's 6 of them, so that would be hexa aqua. Our metal is iron, and it's positive, so it can just stay as iron. And if it's negative for iron, if it's a negative iron complex, it turns to ferrate. So it again uses the Latin name of the element and puts 8 at the end of it. So just remember that for copper, if it's a negative complex, it would be cuprate, and if it's iron, a negative complex, it's ferrate. So hexa, aqua, iron, and our oxidation number in Roman numerals 2. So that would be the name for that complex. So we'll do a couple of other examples now, but hopefully that gives you a bit of a basic understanding of how all of this information comes out of the complex and how it all fits together. So yeah, stay tuned for the next couple of examples. Got a couple of other examples here. We're just going to do the exact same thing. We're going to write down the formula for the transition metal complex, work out the oxidation state of the transition metal in the complex, work out the coordination number, and then come up with the name. So the formula, we have to put the metal first, so in this case it's iron, and then we put the ligands in alphabetical order, so we'll put the chlorine first, and because the chlorido comes alphabetically before cyanido, so we'd have the Cl ligand, there's 4 of them, so that'd be Cl4, and then the Cn, we've got 2 of them, can't spell, so we'd have Cn and then 2, and then we put the square brackets around it, and then the overall charge of the complex goes on the outside. For this one over here, we've got all of the same ligand, so we put the metal first, again can't spell, and then we've got NH3 6 times, and then we put the square brackets, and then the overall charge on the outside. So then if we look at the oxidation states, most of the time the oxidation state you usually work out from the formula, so we'll do it from the formula this time other than the picture. So chlorido is a 1 negative charge, so does the cyanide. So because there's 6 1 negative ligands, that would be like 6 minus, which means that the metal should be 6 plus. However, we have our little extra electrons here, 4 negative, so that's like adding 4 electrons back onto the iron, which then makes it 2 plus. Okay, so the iron is 2 plus. So it should be 6 plus because of the 6 negatives on the ligands. However, because there's a 4 minus on the outside, I'll write that way, and when you add those 4 extra electrons back on, it then brings the oxidation state up to 2 positive for the iron. For the cobalt over here, ammonia, amine, is a neutral ligand, so it doesn't affect the oxidation state. So technically the cobalt should be oxidation state 0. However, there's a 2 positive charge on the outside, so that's like taking 2 extra electrons off, so that makes the oxidation state of the cobalt also 2 positive. The coordination number, we're looking at how many things are attached. So if we do it from the formula this time, we know that these are both monodentate ligands. So if there's 6 of those monodentate ligands, that would be coordination number 6, because each ligand makes 1 bond. The amine ligand, again, although it's a neutral ligand, it still forms a bond. It's monodentate, so because there's 6 of them, that would also be coordination number 6. It's easy to work out the coordination number when it's the picture, because you do literally just count the bonds, but if you're asked to do it from the formula, you will need to remember if it's a monodentate ligand or a bidentate ligand. But most of the ligands you see are monodentate, and it'll just be the oxalato, the oxalate ligand that is the bidentate one if you see that. Then for the naming, so we've got different ligands in this one, and again, like I said, they have to go in alphabetical order. So if we start with chlorido, because that comes in alphabetical order first, there's 4 of them, so that'd be tetra chlorido. And then cyanido, there's 2 of them, so it'd be dicyanido. We've got iron, but it's negative overall, so it has to be ferrate. And then the oxidation state, the end, no numerals, so 2, because we worked out it was oxidation state 2. Run into the space for this one now. So this one, we've got 6 amine ligands, so that would be hexa amine Don't forget the two M's in amine. And then we've got cobalt, which is positive, so it's just cobalt. If it was negative, it would be cobalt 8. And we've got oxidation state 2, so the Roman numeral will be 2. Okay. Sometimes you will get ions on the outside of here. So for example, you could have chloride ions outside of this complex that is sometimes shown. If that's the case, all you have to do is, before you start anything, is remove them, and you just remove them based on what their charge is. So because a chloride ion has a negative charge, if there's 2 of them, that's like 2 minus, so the overall charge of the complex to balance that needs to be the 2 plus, which is what we had originally. If there's for this one, because that's a negative charge, what you probably had here is something like 4 potassiums or something, K4. So potassium has a single positive charge. So if there's 4 of them, that's 4 plus, which means the complex would be 4 minus to balance that out. So you don't always see the external ions shown in the formula, but if you do, that's just how you deal with them. You just remove them based on what their charge is, and then the charge of the complex has to balance that out. Okay, so hope that helps with the naming oxidation state coordination number. We're going to talk a little bit about the colour of transition metal complexes just to finish off, and then that'll be us. So finishing off with the colours of the transition metal complexes. So the reason that transition metal complexes tend to be coloured when we look at them is because they have D to D electron transitions. So D to D electron transitions generally involve quantums of energy being absorbed. So when the electron is promoted from a lower d orbital to a higher d orbital, it absorbs a quantum of energy that will correspond to a wavelength of light that is within the visible region, which is why we can see it with our eyes. So it generally is the colour that you see, it's the complementary colour to that on the colour wheel that is being absorbed. So for example, if I get my colour wheel on page 19 of the data booklet, if we have a substance that appears green-blue, then that means it will be absorbing orange light, which is a wavelength between 605 and 595 nanometers. And then we could calculate the energy of that electron transition by using our E equals LHC over lambda equation. So the reason that you are seeing the colour is because there's a wavelength of light being absorbed that is an energy difference that corresponds to that wavelength within the visible region. So the wavelength is just related to the energy. But just remember, it's the complementary colour that we see. So whatever colour is being absorbed, they're always the opposites. So just as another example, if you have a substance that is green, then it will be absorbing predominantly purple light, so between 380 nanometers and 400 nanometers, and all the other wavelengths are being transmitted, and all those other wavelengths of light that are being transmitted, passed through, not absorbed, combine to give that green colour. So the colour wheel will be your best friend when it comes to colours of transition metal complexes. Also, if you're doing colorimetry and trying to pick a filter, the colour wheel is your best friend there as well, because if you're looking at permanganate solution, which is purple, then you'll need to use a green filter because that's the complementary colour. Because your permanganate's purple, it means, sorry, the dog's shaking. Because your permanganate's purple, it means that you must be absorbing green light. So why do we actually get these D to D electron transitions? Because in the free ions, so if you just have a transition metal ion on its own, you don't get these transitions because all of the d orbitals are degenerate, which means they're all equal in energy. So there's no higher d electron energy levels that are there for promotion to happen to. But when it comes to them forming complexes, what happens is the ligands cause the d orbitals to split in energy. And this is because the ligands are bringing electrons with them, which then repel the electrons that are in the d orbitals on the metal. And it's predominantly the dz squared and dx squared minus y squared orbitals that experience the most repulsion. So what happens is that these two orbitals end up being higher in energy than the other dxy, dyz, dxz d orbitals. So the d orbitals are no longer degenerate. So when the ligands come in and bind to the central metal ion, then the d orbitals split in energy and they're no longer degenerate. And this is why now we can get electrons being promoted from the lower d orbitals to the higher ones. And when that promotion occurs, so let me just promote, let's say I'm promoting this electron here, that's absorbing a certain amount of energy that then corresponds to a given wavelength. And now, depending on what that energy gap is, will then determine what wavelength of light is being absorbed. So typically, if you have a larger gap, more energy is needed for promotion, then it's a lower wavelength of light that's absorbed, because energy and wavelength have an indirect proportional relationship. So if the energy is getting bigger, wavelength's generally getting lower, and vice versa. So therefore, if you've got a smaller energy gap, then you're usually absorbing a higher wavelength of light. Different ligands will cause different degrees of splitting, and this is where the spectrochemical series comes in. It can also be called crystal field theory, as you might have heard that spoken about before. But this is the order of increasing degree of splitting. So the cyanide ligand causes the biggest amount of splitting, which means that if the complex has those ligands in it, then you would expect there to be a really large energy gap between the non-degenerate d orbitals, and therefore we would be looking to be seeing like lower wavelengths of light being absorbed, and therefore the complementary colour would be observed. So just try to vaguely remember which ones cause more splitting than others. Normally you won't necessarily be asked which one causes the bigger degree of splitting than another. You could just be asked to discuss like why you get different degrees of splitting, and it is just because the different ligands cause different levels of repulsion. The cyanide ligand causing the most repulsion, and the iodide ligand causing the least amount of repulsion. Okay, so changing the ligands changes the repulsion of the d or to the d electrons, which then changes the level of splitting between the d orbitals, therefore changing the energy that's absorbed when d electrons are promoted to higher energy levels or higher d orbitals, and therefore changing the wavelength of light that is absorbed. Okay, so changing the ligands on a transition metal complex will change its colour. Okay, the last thing I'm going to touch on will be, I've not got any here, but you quite often get graphs that show you what wavelength of light is being absorbed by a substance. Just look to see what colour is that wavelength corresponds to, and then the colour you see, it will be the complementary colour to that. So just remember, what's absorbed is not what you see, it's the complementary colour of what's absorbed that is actually visible. Okay, the last thing really with transition metals is when they're used as catalysts. So I'll do a little bit on that to finish, just very brief, and then that'll be us. I know I said we were going on to catalysts, but I forgot to mention about some complexes with transition metals are not coloured, and sometimes you can be asked which complex is most likely to be uncoloured or colourless. So this occurs when there are no d electrons in the d subshell at all, or that the d subshell is full, because in those two instances where you have no d electrons or the d subshell is full, there are no possible d to d electron transitions, and it's those ones that usually occur within the visible region. Sometimes you can get complexes where there are no 3d electrons left in the central metal ion, however, based on its oxidation state, but the compound still has a colour. In that instance, it's usually not the metal ion that's causing the colour, it will be the non-metal groups attached to it. So the most common ones are scandium and zinc, because scandium is usually 3 positive as an ion, and so therefore in that instance it has no d electrons, because it would usually have 3d1 and 4s2, and remember the 4s electrons come out first, so then the 4s2 disappears, the 1 3d disappears, and so then there's no d electrons left, so we end up with this scenario where there's no possible d to d electron transitions because there's no d electrons in the subshell. For zinc 2 positive, it's 3d10 4s2, the 4s electrons get lost first, so then it ends up being 3d10 as a 2 positive ion, which means its d subshell is full, and therefore there's nowhere within the d subshell for electrons to be promoted, so therefore no quantums of energy that involve the absorption of wavelengths within the visible region. So just bear that in mind. Then briefly talking about why they're good as catalysts. So they have, because of their d orbitals, they can form intermediate complexes with the reactants. So that's how they provide the alternative route, by making different intermediate compounds. And then because they also have variable oxidation states, it means that they can form bonds with some reactants and then unform the bonds again, so they're pretty flexible in terms of their bonding, which is again leads into them allowing them to form intermediates. This doesn't really get asked much anymore, but I always like to just cover it, add it in, just because it's basic chemistry knowledge really, and anyone that does biology will be familiar with these terms, hetero and homo. So hetero means different, homo means the same. So if it's a heterogeneous catalyst, it means it's in a different state to the reactant. So your reactants might be liquid and your catalyst is a solid, or your reactants could be a gas and your catalyst is a solid. Homogeneous means it's in the same state as the reactant, so usually that would be when your reactants are liquid and your catalyst is always in solution, also in solution. You could also be asked, given like a multi-step reaction, and by multi-step I mean like 3-4 step process, and asked to explain why something has, or how you can see something's being a catalyst. So you're essentially looking for a substance. If it's a catalyst, it's a substance that will be exactly the same at the end as it was of the final step, as it was at the start of the first step. So it's a reactant that remains unchanged through the whole course of, well, at the start and the finish of the reaction. So it will have changed in the middle, because that's what they do, they form intermediates, but by the end of the reaction you should have the exact same thing that you had at the start, and that's a sign that something is acting as a catalyst, when it's this in the exact same state and chemical what's the word I'm looking for here? It has the exact same chemical structure and state as it did at the start of the reaction at the end. Okay, so I think this one's turned out to be a bit of a long one, but there is quite a lot in the transition metal stuff, so I hope you found this useful. If you did, please give it a like, don't forget to subscribe, and I'll see you again soon.